Okay, class, now to understand, just like we did in the blood vessels, we need to look at respiratory formulas. And then we can apply these formulas as we go through, because then we're going to go back to the anatomy in a moment. But I want to do this and then we can apply them. Okay, under the formulas, these are the ones we'll talk about: the ideal gas equation, Boyle's law, and so forth. The ones in red, I'm not going to talk on because we did that in in the cardiovascular. So they're in here, but you can go back and study those in cardiovascular. All right, we start first with the ideal gas equation. The ideal gas equation says that PV equals nRT. P is pressure, volume of the gas is this, N is the number of moles of gas, R is the gas rate constant, T is the temperature in Kelvin. Okay, so this equation here came about for the ideal gas equation. There are certain properties. Some of you may have taken chemistry already. But anyway, that's the formula that we work a lot off of. Okay. Boyle's law says there's an inverse relationship between pressure and volume. Now, if we use this formula, think about it. If I take V to the other side, I've got to divide by V. Okay, got to divide by V. So there's an inverse relationship. Basically, what's it saying? Volume is how much space set amount of number of molecules of gas or liquid occupies. If the volume got larger, but the amount of molecules stayed the same, the pressure exerted by it would go down. Small room, gas in it. Make the room bigger. The pressure will go down as the volume of the room increases. Inverse relationship between pressure and volume. Charles's law, I'm not going to really say much on that. I don't need that in here, but I will say there's a direct relationship between volume and temperature. We go back here, here's volume, here's temperature. The temperature goes up to volume because the gas molecules move further apart. Okay. Dalton's law of partial pressures we need. Okay. Each type gas in a mixture of gas will exert a pressure independent of the other gases in the mixture. So, in other words, if you have a mixture of gases, each will exert an independent separate pressure. But it's a partial pressure because the amount of the pressure exerted by each type is in accordance with the percent present of the mixture times the total pressure exerted by all the gases, called a partial pressure. So let's explain that. All right. Dalton's law. Let's say we have atmospheric pressure. Okay. At sea level, it's about 760 millimeters of mercury pressure per square inch. That's at sea level. That's the atmosphere pulling down because gravity is pulling it down. Or if we use pounds, 14.7 pounds per square. That's at sea level, not on a mountain and not in a valley. The three major gases that we have in the atmosphere are nitrogen, and it's about 78%. O2 about 21%, and CO2 about 0.34. Now that's the percent present in the atmosphere of the gas. So if I wanted to get the partial pressure of these three, what we would do, here's the formula. I would take the 760, which is the total pressure, times 0.21 for O2, because it was 21%, times this for CO2, and times this for nitrogen. You see what I'm saying? So in other words, all we did was to take the total pressure, find out what the percent present is, and multiply, and then we would get what we call the partial pressure. So in the atmosphere, this would be the partial pressure of oxygen, the partial pressure of CO2, and the partial pressure of nitrogen. Okay? That's that particular thing. All right, let's go further. So that's Dalton's law of partial pressures. Henry's law, we go to that next. Okay. The amount of gas that will dissolve in a liquid. Remember now we have fluid that we have to dissolve these gases in because that's we have fluid on the lining of the pipes, and we have fluid in the blood vessels because we got blood. So the amount of gas that will dissolve in a liquid depends on the partial pressure of the gas above the liquid. And that partial pressure is pushing down. Okay? and it depends on the solubility coefficient for the gas or the liquid. In other words, what I'm saying is, how good does that liquid like that particular gas? How good does that particular liquid like that gas? So since our liquid is H2O, water, here would be the solubility coefficients. The solubility coefficients. Now let's look at this. Carbon dioxide, this. Water likes carbon dioxide the best. Then oxygen after that, then nitrogen. See what I'm saying? Oxygen, it likes this the best, then oxygen, then nitrogen. That's why it's not a lot of nitrogen in the blood. That's why it's not a lot of nitrogen in the blood, because water doesn't like to dissolve it that much. So Henry's law says, basically, the amount of gas that will dissolve in a liquid is how hard is the gas pushing down, and how good is that liquid pulling it in. That's the salt. So that's how much it will dissolve. Okay? So I want you to study that. All right. The next thing we talk about is this thing called surface tension. Let's talk about that very quickly. Okay? Because you got my stuff, so you can read on it. This will be in the section. This is under respiratory formulas. Let me say this PowerPoint is called respiratory formulas. Okay, we go further. Surface tension is the elastic tendency of a fluid surface which makes it acquire the least area possible. So if you take water, it wants to acquire the least area possible. You'll bead up, in other words. Let's go back. Surface tension is the expression of the intermolecular attraction of the surface of a liquid in contact with air and so forth. Now, what holds water, AP1, what holds water sticking to itself? Hydrogen bonds. Hydrogen bonds were the intermolecular bonds holding water together, and there were a lot of them. So that surface tension here will come in, and let me pull this down. That surface tension allows even insects. It's so tight that even an insect even the insect is heavier. This is what makes a ship be able to float and so forth. Okay, so I come here, and this is where this particular aspect comes in here. Okay, so I come in here, and this is where this particular aspect comes in, because in the alveoli, you have a lot of water. And so when you inhale, the alveoli get bigger. But when you exhale, the alveoli get smaller when we go. As they get smaller, the water would come close to one another, and the hydrogen bonds would try to collapse the alveolus. The only reason they don't collapse is because of something we're going to talk about, in a chemical that is being produced by the type 2 nematocytes, known as the septal cells, known as surfactant. Surfactant is a chemical that prevents this. It's against surface tension. Otherwise, your alveolus would collapse. So we're going to talk on surfactant, but I want to bring that up as to where this surface tension is a very important concept, and I want you to read on it in the text too. Okay? See, here's alveoli there. All right. So that's our surface tension. See how see how water likes to bead up and those hydrogen bonds? Now here's the formula for surface tension here. Tension equals pressure in the sphere by the radius divided by 2. So I just wanted to show you that. All right. The next formula we come to is a big one, and that's called diffusion. This formula here is called Fick's, F-I-C-K-S, Fick's, F-I-C-K''S, his diffusion equation. This is the equation that says how easily something can diffuse. So let's approach it and look at it here. Diffusion equals to area, the area of the membrane being diffused through. See, it's in the numerator, so the larger the area, the better the diffusion. The DC is called the diffusion coefficient. We'll talk about that. That's in the numerator. The T stands for thickness. That's in the denominator. So if something is very thick, it's harder to diffuse through. And this here is the part which would also be in the numerator in this equation that you know about, because you go from a higher concentration to a lower. So we just use a CO minus CI. It doesn't have to be that, but concentration outside minus inside. It could be opposite. But this is the concentration difference. That's in the numerator. So the larger the concentration difference, the stronger the diffusion force. So let's go back and look at this in simple terms. The larger the area, better diffusion. The better the diffusion coefficient, the better diffusion. The higher the concentration difference, the better the diffusion. The only thing that impedes the diffusion is how thick it is that you're diffusing through. Okay? Now, the diffusion coefficient is the solubility coefficient, which we just did, divided by the square root of the molecular weight of the gas. I'm not going to get heavy into that, but I did go into it to show you. Here's the calculation of the diffusion coefficient. There's oxygen. These were the solubility coefficients. These are the molecular weights of the gases. O2, 2 times 16, O is 16. You can go to the periodic chart. Here's the square root of these molecular weights, and here's the diffusion coefficient. Because the diffusion coefficient, again, let's go back, was the solubility coefficient divided by the square root of the molecular weight of the gas. Now, just looking at it then, you can see that CO2 has the greatest diffusion coefficient, and that's in the numerator. That means CO2 does the best job. We already said that. O2 is next. And then nitrogen, it just doesn't like it much. Okay? So that is diffusion. That is diffusion. Okay? Let's go further. Compliance. Compliance, which we call capacitance with the veins, but it's the same formula, is change in volume over change in pressure. So a small pressure, okay, remember leather pouch balloon. Balloon will blow up bigger with a smaller pressure change, bigger volume than a leather pouch. So compliance is high, and so applying it to the lungs, how easy do the lungs stretch? How easy do the lungs stretch? And we're going to talk about that. Okay? And the compliance of the respiratory system really depends on two things: the surface tension of water and the amount of elastic fibers. Let me say it again to you. The surface tension of water and the amount of elastic fibers. That's what the compliance. The less surface tension of water, the better stretch. The more elastic fibers, the better stretch. So kind of read on that. See what else. Okay, I'm not going to talk on pressure because we already did that in that. So those are the formulas that I want you to know. Those are the formulas. These here too, but this will give an idea once we go back to and start looking at it. All right. So that ends my formulas discussion.